The steam produced in your boiler does a lot of work. It drives turbines. It drives pumps. It provides heat for heat exchangers. And it's sent to many other pieces of process equipment throughout the plant. But in order for a steam system to work efficiently, it must have auxiliary equipment. Now, one of the most important pieces of auxiliary equipment is the steam trap. Steam traps are designed to remove condensed steam or condensate from the steam lines that feed process equipment. Now, to see why this is necessary and how it's done, let's take a look at a simple steam heating system, a radiator. Steam produced in the boiler is sent to the radiator. As steam circulates in the radiator tubes, it gives up some of its heat. Heat used to raise the temperature of a room, for example, and the steam begins to cool. As it cools, some of the steam condenses into water. Now, if this condensate is not removed, it'll begin filling the radiator tubes, blocking the flow of steam and reducing the efficiency of the radiator. But the radiator isn't the only place where condensate is formed. Steam also condenses in the steam lines to the radiator. The temperature of the steam is usually much greater than the temperature outside the pipes. And even though steam lines are insulated, enough heat is lost through the pipes to cause some of the steam to condense. If you've ever boiled water, you've seen this same effect. The ambient temperature, in this case the temperature of the area around the flask, is a lot lower than the temperature of the steam inside the flask. So some of the steam condenses on the sides of the flask and drips back into the boiling water. Now, if you're just boiling water, this isn't much of a problem. But if you're sending steam to various types of process equipment throughout your plant, this condensate can be a big problem. All right, now let's see why. When enough condensate collects in a steam line, a slug of water is formed. Steam rushing past this slug picks it up and pushes it forward. Now, when the steam and slug of water reach a bend in the piping, the steam is able to turn the corner quickly, but the water, because it is denser and heavier than the steam, slams into the wall of the pipe. Now, the loud bang it causes is called water hammer, because it sounds like someone beating against the pipe with a hammer. Now, severe water hammer can even blow a hole through the side of a pipe, harming not only the equipment, but also any people in the area. So, some way must be found to get rid of the condensate that collects in either steam lines or equipment. Now, this doesn't seem like it would be very difficult to do. One obvious solution is to install an open drain pipe at the lowest point in the steam line. Any condensate would drain to the low point in the line where it could be removed. Now, the problem with this approach is that during periods when not much condensate is being formed, the open pipe blows live steam, and the efficiency of the system goes way down. Well, why not put a valve on the pipe to control the flow? Then, when a lot of condensate is being formed, say during startup, the valve can be opened to drain it off. And during periods of low condensation formation, the valve can be closed, preventing the loss of live steam. Now, the major drawback to this approach is that it requires someone to watch the drain and regulate the valve. And since there may well be hundreds of drain points throughout the plant, the number of operators required clearly makes this system impractical. Now, whatever system we have, it should do three things. First, it must discharge condensate without the loss of live steam. Second, the discharge of condensate must be an automatic process, one that does not require operators to monitor the many drain stations throughout the plant. And finally, the system must remove the condensate as fast as it collects. Now, in most cases, the rate of condensation varies considerably. If the system cannot respond to these varying conditions, it'll either discharge live steam or else leave condensate in the steam lines, risking serious damage from water hammer. Now, in addition to these criteria, removing condensate without loss of steam, removing it automatically, and removing it under variable flow conditions, the system must also be able to remove any air in the steam lines. Now, the biggest problem with air happens when a system has been shut down for a while and air gets into the piping. Then, when the system is started up, the air stays in the pipe. Now, if this air is not removed, it'll decrease the efficiency of the system and increase the chances for corrosion. Now, the device that does all of this, that automatically drains condensate and discharges air from steam lines, is the steam trap. But before we examine the various types of steam traps to see how they work, let's first look at a typical steam trap station and see where it fits into the steam system. Now, first is the steam line or process equipment. Coming off the lowest point of the steam line or equipment is a drip line where condensate collects. The drip line should contain a dirt pocket. This dirt pocket will collect and hold some of the larger particles of dirt or scale that may be in the line. Next is a trap inlet valve that isolates the inlet side of the trap from the steam line or steam equipment. After the inlet valve is a strainer that removes any scale or dirt in the line. It has a blow-down valve that can be opened to clean out the strainer. The trap itself is next. Then there is a test connection with a valve. Opening the test connection allows us to see what the trap is passing. There is an outlet valve here that separates the trap from the downstream piping. The downstream piping may discharge to the atmosphere, or it may discharge to a condensate return line, like it does here. And finally, there is usually a bypass line with a valve enabling us to bypass the entire trap station. Now, we've shown you what you might find in a steam trap system, but the arrangement of these parts can be different. Also, some parts may be left out. There may not be a bypass valve, or there may not be a test connection. All right. We know that steam traps trap steam while letting air and condensate out. Now we're ready to see how they do their job. But first, turn off the tape and review the material that we've covered so far. We've already looked at how condensate is formed and how it affects steam systems. We saw the need for steam traps, devices that automatically drain condensate and remove air from steam lines. We said that steam traps operate under all conditions, from low flow to full flow. And we also saw where steam traps are located, in the drip line coming off a low point in a piece of process equipment. Well, now it's time to see just how these steam traps work. All steam traps have some sort of mechanism to sense the presence of steam and stop its flow, while still allowing condensate and air to pass. Now, there are three basic ways of doing this. First, traps can respond to the temperature difference between steam, which is relatively hot, and condensate and air, which tend to be relatively cool. Steam traps that operate on this principle are called thermostatic traps. The most common thermostatic trap is the bellows trap. Second, traps can respond to a difference in density. Steam is less dense than condensate, and traps that use a density differential to separate steam and condensate are called mechanical traps. The most common mechanical traps are the float trap and the inverted bucket trap. Of course, since the densities of air and steam are very close to one another, mechanical traps usually require a second method of separating air from steam. Now, this second method is often a thermostatic device. Third, traps can respond to the heat energy of condensate. When the pressure of hot condensate is lowered, some of the condensate flashes to steam. Now this flash steam, as it's called, can be used to close a trap. Traps which use flash steam this way are called thermodynamic traps. Now, the most common thermodynamic traps are the disc trap and the piston trap. Okay, so we've seen that traps are categorized as thermostatic, mechanical, or thermodynamic. And we've briefly seen 5 different traps. Now, let's see how they work. The bellows trap is a thermostatic trap. That means it operates on a temperature difference between condensate and steam. From the outside, you can't tell very much about the trap. But in this cutaway, you can see the trap internals. The bellows is here. It's filled with a mixture of water and alcohol that boils at a fairly low temperature. At the bottom of the bellows is the valve that opens and closes the trap. This simplified drawing makes it easier to see how the trap operates. Let's assume there is cool condensate at the trap inlet. When condensate fills the inside of the casing, the bellows will be compressed and the trap valve open. The condensate simply flows through the trap. But when steam is about to enter the trap, the condensate in front of the steam will be hot enough to boil the liquid inside the bellows. The bellows will expand, closing the trap valve. The valve will remain shut as long as there is steam or hot condensate at the trap inlet. But when the condensate inside the trap cools down, the vapor inside the bellows will condense, causing the bellows to compress and the valve to open. Thermostatic traps then alternate between periods of discharge and no discharge, depending on the temperature of the condensate. This means that the discharge from a thermostatic trap will be intermittent rather than continuous. Thermostatic traps are the best type of trap at discharging air. Air is usually cooler than steam, so as it fills the casing, it will not cause the liquid inside the bellows to boil. The bellows remains compressed, the trap valve stays open, and the air is discharged. Because the bellows-type thermostatic trap gets rid of air so easily, it's ideal for situations where large quantities of air are present. But these traps are limited by pressure. Typically, they cannot be used where the pressure is very high. If they are, the bellows may collapse. Now, another trap limitation is its susceptibility to water hammer, which can rupture the bellows, causing the trap to fail open. Now, some bellows traps have a shroud or covering around the bellows to protect them from water hammer. Thermostatic traps should never be covered with insulation. Insulation slows down the heat loss, and it would then take too long for the trap to cycle. If bellows traps are installed so that they drain thoroughly, they won't freeze. Now, this makes them an excellent choice for outdoor applications. The second type of trap we'll discuss is the mechanical trap, but I think we've covered enough for now. So turn off the tape and review the material that we've discussed so far. In the last segment, we looked at the operation of a bellows-type thermostatic trap. Now, in this segment, we'll discuss mechanical traps, the float trap and the inverted bucket trap. Now, remember, mechanical traps respond to a difference in density between steam and condensate. A typical float trap looks like this. In this cutaway, you can see the trap internals. The float, for which the trap is named, is here. A rod connects the float to the trap valve located here. Condensate and steam enter the trap here at the inlet. Condensate is discharged here at the trap outlet. In this drawing, you can see the inlet and outlet a little more easily. As condensate enters the trap, the float rises along with the condensate level. At first, nothing much happens because the float and rod are adjusted so that the trap valve stays shut until the condensate level is well above the outlet of the trap. This allows some water to remain in the trap as a seal, preventing live steam from escaping. When the condensate level is above the trap outlet, the trap valve opens. If there is a small amount of flow into the trap, there will be a small amount of flow out. If flow into the trap increases, the float will rise higher, the trap valve will open wider, and flow out of the trap will increase. When steam is about to enter the trap, the condensate in front of it will be hot. Steam enters and fills up the inside of the trap. Less and less condensate is formed. The float drops to its lowest position, and the valve closes. Some water remains in the bottom of the trap, covering the outlet and preventing steam from escaping. A float trap, unlike a bellows trap, responds directly to the amount of condensate being produced. As long as condensate is present, the discharge from a float trap will be continuous rather than intermittent. Now, air can cause problems in a system with a float trap. If the trap fills with air, the float will be at its lowest position, and the trap valve will be shut. Also, the air inside the trap will prevent any steam or condensate from entering. The trap becomes air-bound, unable to operate. Since some air is found in almost all steam systems, a lot of float traps have a thermostatic bellows inside to vent the air. These are known as F&T, or float and thermostatic traps. In this example, the bellows is located in front of the trap inlet. When air collects inside an F&T trap, the bellows will compress because air has less heat energy than steam or hot condensate. The compression of the bellows opens the vent valve, allowing air to leave the trap and allowing condensate to enter. Some of the more common problems with float-type traps are a clogged inlet or outlet, dirt on the seat of the trap valve, a leaking float, and freezing. Now, a clogged inlet or outlet will cause condensate to back up, allowing little or no discharge at the outlet. Dirt on the seat of the trap valve prevents the trap valve from fully closing, resulting in steam blowing through the trap. And sometimes a float will leak. Now, if this happens, the float fills up with condensate and sinks. The trap will then fail closed. And finally, since float traps never empty completely, they can freeze. But keep in mind that steam traps that are in operation rarely freeze. The warm condensate flowing through them usually prevents freezing. See, the real danger occurs when the trap system is shut down and the condensate cools. So, if you shut down a trap system that has float traps, be sure to drain all the water out of the casing. Now, most float traps are equipped with a drain plug for just this reason. Now, the third type of trap we'll discuss is the inverted bucket trap. Like the float trap, the inverted bucket trap is also a mechanical trap. In this cutaway, you can see the inverted bucket, which looks like an upside-down can. It has a small hole in the top, which you can't see here, but which you'll be able to see in a moment. A connecting rod connects the bucket to the trap valve. The trap inlet is located here at the bottom of the trap. Condensate is directed to the upper part of the trap through a pipe. The trap outlet is here on the top. In this drawing, which we'll use to show how the trap operates, you can see the small hole here in the top of the bucket. Like other mechanical traps, the inverted bucket trap has condensate in the bottom to act as a seal. With condensate in the trap, the bucket is in its lowest position and the trap valve is open. Cool condensate enters the inlet pipe. It flows into and then out of the bucket, traveling up between the outside of the bucket and the inside of the casing wall. Finally, it flows out the trap valve. What about steam? As steam and hot condensate enter the trap inlet, the steam collects in the top of the bucket rather than the bottom like condensate. The bucket becomes buoyant and rises, causing the trap valve to shut. Then, some of the steam escapes through the hole in the bucket and condenses. The rest of the steam condenses inside the bucket. The bucket loses its buoyancy and sinks. This opens the trap valve, allowing the condensate to be discharged. Since the inverted bucket trap operates on a cycle, opening in the presence of condensate and closing in the presence of steam, the discharge from the trap should be intermittent. If you observe continuous discharge from an inverted bucket trap, there may be a problem. The inverted bucket trap is good at removing fairly small volumes of air. When air enters the trap, it fills the bucket, causing it to rise. This closes the trap valve. But some of the air is able to escape through the hole in the top of the bucket. As it does, the bucket loses its buoyancy and sinks, opening the trap valve. The air is then discharged from the trap outlet. Since the hole in the inverted bucket passes only a small amount of air, these traps should not be used where large volumes of air must be removed. Since inverted bucket traps and float traps are both mechanical traps, they have similar maintenance problems. There are some differences, though. Now, you may recall that when the float in the float-type trap sank, the trap failed closed. However, if the bucket in an inverted bucket trap develops a hole larger than the one it already has, steam will escape too fast for the bucket to become buoyant, and the trap will fail open. In general, though, inverted bucket traps can be used over a wide range of pressures, and they have adequate air removal abilities for most systems. For these reasons, inverted bucket traps are found in many industrial applications. Okay. Well, so far, we've seen how thermostatic and mechanical traps operate, and we've seen some of the limitations of each type. Now, before we discuss the operation of thermodynamic traps, turn off the tape and review the material that we've covered so far. So far, we've discussed thermostatic and mechanical traps. Thermostatic traps, you remember, operate by sensing the temperature difference between steam and condensate. Mechanical traps, on the other hand, rely on the density difference between steam and condensate. And now, we'll discuss thermodynamic traps. We'll see how they operate, and we'll talk about some of their more common maintenance problems. Thermodynamic traps depend on flash steam to operate. Now, in order to understand what flash steam is, let's look at how steam is produced. Water in a boiler is heated until it turns into steam. The same thing is happening here. Water in this flask is being heated to the boiling point, and bubbles are being formed. The bubbles in the water are steam bubbles. Now, this kind of steam is called live steam because it is coming from water that's being heated. Most people think that you can see this steam, but what you actually see is the vapor caused by the steam condensing. Okay, So the steam bubbles here are live steam. But there is another type of steam called flash steam. It occurs when the pressure of hot condensate is reduced. Now, to demonstrate flash steam, we remove the flask from the heat source. As the water cools, it stops boiling. Live steam is no longer produced. If we wanted to produce more live steam, we'd simply add more heat. But instead, we're going to connect the flask to a vacuum pump and lower the pressure inside the flask. This sudden drop in pressure will be similar to the pressure drop inside a thermodynamic steam trap. Notice that the water begins to boil again, but no heat is being added to the water. The pressure drop alone is enough to cause the water to boil. The steam we are now producing is flash steam. Shortly, we'll see how flash steam is used to close a thermodynamic trap. This is a typical tilting disc type thermodynamic trap. It's one of the simplest of all trap designs. With the top removed, you can see the only moving part, the disc. The trap inlet is here, and the outlet is here on the other side. Now, to see how the disc trap operates, let's use this simplified drawing that shows a front view of the trap. The disc is here. One side of the disc moves up and down inside the trap. When condensate enters the trap inlet, it pushes the disc up and flows out the discharge. The flow of condensate past the disc creates a lower pressure area around the disc. Now, when steam is about to enter the trap, the condensate in front of it will be hot. And what happens when this hot condensate reaches the low pressure area? Right. Some of it flashes to steam. This flash steam chokes off flow and builds up pressure above the disc. The disc snaps shut, closing the trap. The disc will stay shut until the flash steam condenses, lowering the pressure above the disc and allowing the disc to reopen. The disc opens and closes with a distinctive click, and since the disc cycles between open and shut, the discharge from the trap will be intermittent. Tilting disc traps are good at removing air from steam lines. Air at the trap inlet simply pushes the disc up and is then discharged through the trap outlet. Only steam or hot condensate will close the disc. The last trap we'll discuss is the piston-type impulse thermodynamic trap. The one you see here is a combination trap and strainer. The trap is basically made up of a piston valve that moves up and down inside a control cylinder. Since the internals of this trap are a little more complicated than the other traps we've looked at, let's use this drawing to identify the trap parts. The trap inlet is here, and the trap outlet is here. The piston itself is in the middle of the trap. The lower part of the piston is tapered and acts like a valve to close off flow from the inlet to the outlet. You can also see that the piston has a hole drilled through it. At the top of the piston is a ring called the piston disc. And at the top of the piston disc is a smaller opening called the control orifice. The piston moves up and down inside a control cylinder. When condensate enters the trap, it pushes up against the piston disc. The piston rises, and condensate flows past the tapered section of the piston and out the discharge. There is also some flow past the piston disc, through the control orifice, down the middle of the piston, and out the discharge. This flow is called control flow and is used to close the piston valve. Let's see how. Inside the trap, pressure is highest at the inlet. It drops somewhat in the area above the piston and is lowest at the trap outlet. So, when hot condensate enters the trap and is discharged, some of it flashes to steam above the piston disc. Not all the steam can get through the control orifice. The pressure above the piston disc increases enough to snap the piston shut. Even with the piston shut, though, there is still control flow through the control orifice. The piston remains shut as long as the control flow of condensate continues to flash. When the condensate cools, the pressure above the disc drops and the piston reopens. Piston traps, like disc traps, are either open or closed, depending on the temperature of the condensate. This means their discharge should be intermittent rather than continuous. And piston traps, as is true of most thermodynamic traps, have excellent air removal capabilities. If air is present at the trap inlet, the air will simply lift the piston and be discharged through the trap outlet and through the control orifice. Air will continue to be discharged until steam or hot condensate reaches the trap. The most common problem with thermodynamic traps occurs when the disc or piston wears out, allowing steam to blow by. And another operating problem is dirt lodged in critical areas, such as the disc or piston seat. This also causes steam to blow through. Weather conditions are another source of operating problems. Rain, for example, can cool the outside of a trap so much that it'll open and close too often. Now, some manufacturers have developed traps with double-walled bodies that allow steam to circulate around the trap internals. Now, this maintains even temperature within the trap, even under adverse weather conditions. A metal insulating cap is another way to maintain even temperatures. Now, these caps act like storm windows to hold in any heat, and they have the added advantage of not using any steam while they work. Keeping thermodynamic traps warm improves their efficiency. Unlike thermostatic traps, thermodynamic traps can and sometimes should be insulated. Now, if you have any doubt about the characteristics of a particular trap, read the manufacturer's literature on that trap. Manufacturers often provide all the information you need to know in order to properly maintain the traps in your plant. Well, now that you know how the different steam traps operate and you've seen some of their maintenance problems, you're ready to get into troubleshooting. But first, turn off the tape and review the material that we've covered so far. So far, we've looked at the internals of 5 types of steam traps, and we've seen how they operate. But when, as part of your job, you have to inspect a trap to determine if it's working properly, you're not going to be able to see inside. And just looking at the outside of the trap isn't going to tell you very much, especially if the trap doesn't discharge to the atmosphere. Also, in order to determine if there's something wrong with a particular trap, you must know whether the rest of the trapping system, that is, the pipes, strainers, and valves, are working properly. A failure of any one of these components could make the trap look like it needs repair or replacement, when in fact there's nothing really wrong with it. In this segment, we'll be talking about ways to ensure that the trap system is working properly, and we'll discuss specific techniques for troubleshooting steam traps. Techniques based on sight and sound. As with other mechanical equipment, the more experience you have observing steam traps under a variety of operating conditions, the better you'll be at determining if they fail. why they fail, and what's wrong with them. Now, you gain some of this experience while performing periodic examinations of traps. These examinations, or surveys, are conducted to discover traps that have failed. As part of your survey, keep a record of trap failures. Now, this record will alert you to those traps that have an unusually high failure rate. Typically, traps should last an average of 3 or more years. Now, any trap that fails repeatedly within a 3-year period should be investigated and the cause of the failure determined. There are 2 steps to performing a trap survey: checking the trap system and checking the trap itself. In the trap system, any failure of the pipes, valves, or strainers associated with the trap could make an operating trap appear to have failed. This is sometimes referred to as a trapping problem rather than a trap problem. Well, what do you look for when trying to see if the trapping system is working properly? Well, here are some checks that experienced mechanics routinely perform. Make sure the steam pressure at the inlet to a piece of equipment matches the nameplate data on that equipment. Check to see that the drip lines are connected to the lowest point in the system. Check to be sure the drip line is sloped down toward the trap and that there are no dips or pockets that would slow the flow of condensate. Make sure the condensate line to the trap is large enough to carry the condensate that's being produced. The drip line to the trap should never be smaller than the trap inlet size. Similarly, the condensate return line from the trap must be large enough to carry both the condensate from the trap and any flash steam that is formed. Discharge lines should be at least as large as the trap outlet. Check the back pressure at the trap outlet to make sure it's not too high. If several traps discharge to a common return line, the line should be large enough to handle the discharge from all traps without developing excessive back pressure. Finally, make sure the trap strainer has been blown down. Usually opening the strainer blowdown valve 1 full turn and then closing it will provide enough flow to clean out the strainer. Now, as you make these checks, keep in mind that ideal conditions are rarely found, so it's a good idea to check the operating history of the trap. For example, now, you may find a drip line that doesn't tap off the lowest point in a system, but in checking the records, you discover it was installed that way 15 years ago, and the trap system has operated without trouble ever since then. Now, in this case, chances are the drip line isn't the problem. Further checking may reveal that on several occasions in the past, the strainer was found to be so severely clogged that it had to be replaced. Now, this tells you the problem may be excessive scale formation in the system. Learning to check the operating history like this can be a big help in uncovering problems. Now, once you've checked for trapping problems in the system, the next step is to check the trap itself. Now, the easiest type of inspection to make, one that doesn't require any special instruments, is a visual check. But before you begin a visual inspection, you need to know what flash steam and live steam look like. Now, flash steam is the lazy vapor that forms when hot condensate is discharged from the trap. The normal discharge from a trap consists of a center core of hot condensate with flash steam circling the outside. Now, live steam, steam produced in the boiler, is usually discharged with more force than flash steam. There is no center core of condensate, and at the pipe discharge, there is a gap between the pipe and the steam. The ability to distinguish between live steam and flash steam is essential in knowing whether a trap is operating properly. In fact, it'll usually be the first thing you look for when inspecting a trap. If the trap discharges to the atmosphere, it's a simple check to make. Simply observe the trap discharge. If the trap discharges to the condensate return line, as this one does, First, close the trap outlet valve. Then, open the test connection. The trap should be discharging hot condensate with some flash steam, as you see here. If the trap is discharging live steam, then you know the trap's not working properly. It needs either repair or replacement. Once you know what the trap discharges, see how often it discharges. Does it discharge continually or intermittently? If the discharge is intermittent, time the cycle rate and compare it with what the manufacturer says is normal for that type of trap. Remember that different types of traps have different cycle rates. Inverted bucket traps, for example, like this one, are designed to discharge intermittently. So a continuous discharge could indicate serious problems with the trap. Float traps, on the other hand, are designed to discharge continually, as long as there's a constant flow of condensate to the trap. Now, a visual inspection may tell you everything you need to know to pinpoint a trap problem, but many times it won't. And if the trap doesn't discharge to atmosphere and there is no test connection, then you won't even be able to make a visual inspection. You may want to inspect the trap by listening to the sounds it makes. An instrument of some type is helpful in transmitting the sound from the trap to your ear. A sounding rod or even a screwdriver will work all right, but a stethoscope is probably the best tool to use. Place one end of the instrument on the trap body and the other at your ear. It may take a little practice, but you'll soon learn to recognize the sounds made by the trap internals. If you cannot hear any flow through a mechanical trap, it may have failed shut. It's hard to tell for sure because some mechanical traps will, under light load conditions, pass only very small amounts of condensate. Now, this can be very difficult to hear. If possible, visually check the flow to determine whether there is no flow or just low flow. Don't forget to protect your eyes. Here you can see that some condensate is being discharged from upstream of the trap. If condensate is also discharged downstream of the trap, as it is here, then we know the trap has not failed shut. In mechanical traps, you will hear the flow of condensate as the bucket or float cycles. If these traps fail open, you'll hear steam whistling through the trap. In thermodynamic traps, a click will be heard as the disc or piston opens. As long as it remains open, you should hear a rumbling sound as the condensate passes through the trap. Then, as the trap closes, there'll be another click. And these sounds will be repeated as the trap cycles. Failure of a thermodynamic trap will be characterized by a rapid chattering of the disc or piston as the steam blows through the trap. Failure of thermodynamic traps in the closed position, where you would hear no sound at all, is rare. But if the trap does not seem to be opening or closing, you can usually open the strainer blowdown valve and sample the contents in the pipe leading to the trap. If the blowdown line passes a lot of condensate, but the trap doesn't, the trap has probably failed shut. In thermostatic traps, you will hear the periodic discharge of condensate as the trap cycles. Absence of sound may mean that the trap has failed shut. However, check the flow to and from the trap to be sure. If the bellows ruptures or the seat wears, you'll be able to hear the steam blowing through the trap. Now, So far, we've discussed visual and sound checks of traps. A third method, temperature checks, can also be used, and we'll discuss the temperature method in the next segment. But before we do, stop the tape now and review your text. In the last segment, we discussed two ways to survey or troubleshoot steam traps, the visual method and the sound method. The visual method requires observation of the trap discharge. The absence of any discharge usually indicates that the trap has failed shut, while discharge of live steam probably means that the trap has failed open. Now, we also explained that while the visual method is the easiest to use, there are situations where you simply can't use it, such as when the trap discharges to a closed condensate system and there is no test connection. Now, we pointed out that where it is difficult or impossible to see the discharge from a trap, the sound method can be used. A stethoscope or other sound detecting device is used to listen to the trap internals. But you'll often find yourself in situations where loud background noise drowns out any sounds the trap is making. In that case, you may want to use the third troubleshooting technique, temperature. Measuring the temperature of the trap inlet and outlet piping is one of the most effective troubleshooting methods. But it usually requires more time than either the visual or sound method. To use the temperature method, you must first understand that the pressure of steam has an effect on the temperature of the steam. The higher the pressure, the higher the temperature. In your text, you'll find a chart that shows the temperatures associated with various steam pressures. Now, unfortunately, you can't just take two temperature readings and then automatically know whether or not the trap is functioning properly. That's because without knowing the steam pressure on both sides of the trap, you have no way of knowing what the temperatures are supposed to be. So, to use the temperature method, you must first determine the steam pressure at the inlet and outlet of the trap. Once you know the inlet and outlet pressures, you can use the chart in your text to find the temperatures that correspond to these pressures. Now, you also have to consider that the temperature readings you take will tell you the temperature of the outer surface of the pipe rather than the steam itself. Since there is a heat loss across the pipe, the readings you get will be about 5 to 10% lower than the temperature of the steam. Now, the chart in your text that gives the steam pressure and temperature relationships also gives the allowable range of temperatures expected during troubleshooting, and it takes into account the heat loss that occurs at the pipe surface. So, if you know the steam pressures at the steam trap inlet and outlet, and you know the range of temperatures you can expect, the next step is to measure the temperature and see if you get the expected result. Now, to do this, you'll need a pyrometer or similar temperature sensing device. Be sure to clean the areas where you'll place the pyrometer. You'll get good results with a wire brush or a file. Cleaning is necessary to ensure an accurate temperature reading. After you clean the areas, go ahead and take a temperature reading at the trap inlet. Be sure to hold the pyrometer in place long enough to allow it to respond properly. Repeat this procedure at the trap outlet. When you've taken both measurements, write them down on a piece of paper. Remember that we're comparing the temperature we obtain with the allowable temperature range from the chart in the text. If, at the trap inlet, the actual temperature is too high, then the pressure at the trap inlet must be higher than you originally thought. So, recheck the steam pressure. If the trap inlet temperature is within the allowable range, conditions are normal. If the trap inlet temperature is too low, the trap inlet or outlet valve may be closed. There may be an obstruction in the line, or you may have an incorrect pressure reading. What often happens in situations like this is that you're working on a system that you're familiar with. Since you know what the pressure should be, you just assume it's right and you don't bother to measure it. Now, if you really know the system, it's okay to do this, as long as you realize that if you get a low inlet temperature reading, you're going to have to go back and get a true pressure reading. Okay, let's assume you have a true pressure reading and you're measuring inlet temperature. You get a reading that you think is low. When you compare it with the expected temperature, you find that it is too low. Now, what's this mean? Well, it could mean one of several things. The trap itself may have failed shut. The inlet or outlet valves may be closed, causing condensate to back up in the line, or there may be an obstruction upstream of the trap. Now, each of these possible causes should be checked out. Verify that the inlet valve is open. Make sure the outlet valve is also open. Then open the test connection and see if the trap is cycling properly. And finally, blow the strainer down to make sure it's not clogged. If, after performing these checks, inlet temperature is still low, you'll have to take temperature measurements upstream of the trap until you get a reading within the allowable limits. Now, if the line is insulated, then you'll have to remove the insulation. Remember, when taking temperature readings, to wire brush the areas where you're going to put the pyrometer. Then, go ahead and take the reading. If it's still too low, move farther upstream. Now, in this case, we have to remove insulation before taking another reading. Make sure you wear the proper protective equipment whenever you remove or replace insulation. If this reading is now within the expected range, there's probably an obstruction between this point and the last place you measured. Be sure to properly isolate the trap system before removing the obstruction. Once it is removed, replace the pipe insulation and return the system to operation. Okay, now let's consider the temperature at the trap outlet. If the trap outlet temperature is too high, the trap may have failed open or the outlet piping may be clogged. Use either a sound or visual inspection to see if the trap has failed open. If it has, it must be replaced or repaired. If the temperature at the trap outlet is within the allowable range, conditions are normal. If the temperature is too low, the trap may have failed shut. Open the strainer blowdown and check the amount of condensate upstream of the trap. If a lot of condensate is being discharged, then the trap has probably failed shut. If mostly live steam is discharged, the trap is probably okay. Now, another possibility is that the condensate flow in the drip line is so small that very little condensate is being discharged. Now, this condition is normal and is not a problem. Well, we've now covered the three methods of surveying or troubleshooting a trap. Although each method was covered separately, in practice you'll probably use several of the methods together. Now, that way you get a more accurate picture of the condition of the trap. Much of the time, one or more of these techniques will be all that you need to solve a particular trap problem. But sometimes you'll repair or replace a trap only to find that it fails the same way it did before. So, never assume that the problem has been solved until you've located the cause of the failure. One of the major causes of trap failure is oversizing. Oversizing is explained in your text, but the important thing to remember here is that if the trap fails consistently before it is 3 years old, check out the possibility that the trap is oversized. When installing a new trap, do not use size as an indication of capacity. Check the manufacturer's literature to be sure that the trap being replaced and the new trap have the same design specifications. This may be possible even though the traps are physically different. If you are installing just one union fitting, place it downstream of the trap. Installed this way, a leaking union will blow condensate instead of steam. If your plant has thermodynamic traps with outside exposure, consider fitting each trap with a special bonnet cover provided by some manufacturers. These bonnet covers increase the efficiency and life expectancy of thermodynamic traps. More information on these bonnet covers is found in your text. As a rule, steam traps are removable devices which, when used properly, give excellent service over a long period of time. The key to good service is the statement, when used properly. Now, your job as a mechanic is to ensure the traps are installed and maintained properly. In most cases, this is a big job, but there is a reward. Better maintained and installed traps mean less work for you in the long run.